Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Design News webinar. Check out these new moves in motion control, sponsored by igus, PI, and Rise Robotics, and broadcast by Informa. I'm Rob Spiegel, and I'll be your moderator today. We have just a few announcements before we begin. This webinar is designed to be interactive. On the right-hand side of your screen, you'll find the Navigation Center, which will allow you to learn about today's speakers, download resources, and participate in the Q&A section that takes place at the end of our presentation. If you experience any technical difficulties, refresh your webinar console within your browser window, or type your issue into the Q&A, and we will be glad to offer one-on-one assistance. Before you leave us today, please complete our webinar survey, as your feedback will provide us with valuable information on how we can improve future events. Lastly, we're so glad to have you joining us remotely today, but did you know we also offer opportunities to learn and connect in person at our live events? Please consider joining us August 26 and 27 in Boston for Med Device Boston. You can learn more about the event at the resource widget. Now on to the presentation. Today's topic, for discussing today's topic is Matt Price, Director of Applied Research and Development at PI, Hiten Sonpal, CEO of Rise Robotics, and Mike Patterson, Director of Regional Sales, Energy Chain Systems at igus. To read about our speakers, please visit the Info tab in your Navigation Center. From here, I'm going to pass it over to each of our speakers to offer some information on their background and relevancy to motion control.
Hello, my name is Matt Price. I'm the Director of Applied Research and Development here at PI. I'd like to take a few minutes to walk you through some background on PI, what we do, and how it ties into the global community of precision automation. So PI is a part of the Herbiger Group. We have 20 locations with 15 subsidiaries. We're a global leader in precision automation with a global footprint all around the world. I'm based in Irvine, California, where we have applied research and development. We're headquartered outside of Boston in the US at Shrewsbury, Massachusetts, with our global headquarters in Karlsruhe, Germany. And there's many companies that fall under the Herbiger Group and under PI, including ACS. As a company specializing in precision automation, there's skills that are of interest, and I think where we have a high degree of relevance for potential automated solutions. Those skills, if you were to hold up your finger and look at the ridges, the spacing between your finger ridges is typically in the neighborhood of 500 microns. When we start to speak in units of microns, nanometers, microradians, arc seconds, and sub-microradians, we're in the area where now PI makes automation solutions for these kinds of applications and end markets. So what does the anatomy of a PI solution look like? It again starts with this level of precision. This is where we specialize with piezo and automation technology. For almost any kind of load, including human loads, you can see one of our concepts here with the hexapod. And at right, you can see one of our integrated photonic solutions carrying a fiber array unit. We have a large 16-axis system, and we have a wafer stage for metrology and inspection. Below that, our solutions can be pure translation or pure rotation. They can be complete integrated multi-axis solutions. You're looking at free space optical communication equipment with the fast steering mirror. You're looking at a microscope objective used in autofocus, and then you're seeing a complete integrated solution with the piezo galvo for laser materials processing. Now, that gets combined generally with motion control drive and algorithmic process intelligence embedded. We'll be talking about that today. And you can see some of the technologies that we've developed in the recent past, from integrated photonics to active piezo shaping to complete control systems with embedded machine learning and adaptive algorithms. And Some of our projects even end up on mission-critical applications on Mars. So we have the broadest and deepest catalog of vertically integrated piezo and electromagnetic drive and control technologies, and everything you're seeing here and beyond is a part of the scope of what we do. So currently we have 200 plus R&D engineers. We put a lot of emphasis on developing the next generation of technologies. Again, we'll talk about it in this webinar. We have 400 new developments every year. 10% of our cells gets reinvested into R&D, and we've had steady double-digit growth since our founding over 50 years ago. We have 500 patents. Multiple patents have been applied for from my group, and we specialize in the categories and topics that you see here, from piezo, air-bearing motion, drive, parallel kinematic, hexapod sensor, algorithmic process, and machine learning to magnetic levitation technologies. Thank you for joining this talk. I'd now like to pass to Hiten.
Hi, I'm Hiten Sonpal, CEO of Rise Robotics. I've been with the company about 2 years, brought on board by the founding team to help take them to the next stage of growth. Prior to joining Rise Robotics, I was at iRobot for a large portion of my career, where teams that I led generated over 2 billion in revenues, shipped 9 million units across 20 products. I'm here to talk about what we're doing at Rise Robotics. We're focused on modernizing one of industry's oldest technologies, which is hydraulics. Our core technology, hydraulics, is a new category of high force electric actuation designed to replace traditional hydraulic systems. We work with OEMs, tier 1 suppliers, and defense organizations to help bring more efficient digital controlled motion systems into industrial and mobile equipment. And this work has given us a front row seat to many of the changes happening across machine design today, particularly as equipment becomes more electrified, connected, and autonomous. It creates opportunities to rethink technologies that have remained largely unchanged for a generation. I'm looking forward to discussing those trends with today's panel, sharing what we're seeing from customers and partners, and talking about where motion control is headed as the next generation of industrial machines comes to market. Can we move to the next slide? Thank you. I think I forgot the controls here. So our company is MIT affiliated. We're based in Somerville, Massachusetts, been around since 2011. Spent the first part of the company on early prototypes focused on human augmentation, and then finally landed on our belt-rolling technology as our core product. Through 2019 to 2023, we've been validating our technology, getting into partnerships, making investments in maturing the tech. And since 2024, which is when I joined, we're getting ready for commercial readiness. Up until 2024, our biggest customer was the Air Force. But since then, we've landed our first commercial customer. And this year, we're scaling and getting into sales and global distribution. The challenge with traditional hydraulic systems is that they lose energy. Traditional hydraulic systems are on average 25% efficient. So 3/4 of that energy is wasted as heat. They require ongoing maintenance. That's because seals will leak and age. They leak hydraulic fluid, which is poisonous and dangerous to the environment. And at high pressure in around high pressure hydraulic systems, it's actually dangerous for humans. So you have to wear PPE. They do add substantial complexity to the system. I know it's hard sometimes to see the complexity in a legacy system, but folks that we work with that design new machines find it very easy to add electronics, mechanical systems, software. And then when they have to add hydraulics, the complexity shows up because now they have to deal with hoses, liquids, pumps, reservoirs, radiators. And these are things that they don't need in the traditional, in electrical systems that are being used to design most new machines today. And hydraulics limits the electrification of existing machines because of the inefficiency. For mobile systems, the battery sizes end up being huge because 3/4 of that energy, well, a lot bigger than they need to be because 3/4 of that energy is wasted as heat. And finally, they limit digital control. Even though sensors can be added to hydraulic systems to measure what's happening very precisely, the ability to control them precisely is still limited because you're still using valves, you're using fluid, and ultimately you're controlling velocity and then trying to solve for position often. And that is a problem in systems that are inherently squishy. So what we've done at Rise Robotics is we've invented this new technology we call belt-rollics. And we've been inspired by human muscles. We've taken out the liquid from hydraulic systems, and instead of pushing pistons, we pull pistons using belts. That's what the inside of one of our actuators looks like. We use belts and pulleys for most of the motion and electric motors. And all of the technologies we use are well understood. So the wear of belts, the wear of bearings, motor design, all of these are tried and tested technologies that we've assembled together. Our systems are 3 times as fast as hydraulic systems, 3 times more efficient, 3 times as durable, 20% lighter because we don't have any fluid on the inside. We have up to half the operating cost at the system level. Certainly we have no fluids, and we're 100% digital. We're also as strong as hydraulics. Last year, we set the Guinness World Record for building the world's strongest robotic arm prototype. And our technology enables electrification, as I mentioned, because we're so much more efficient. But we also enable teleoperation because we are drive-by-wire out of the box, and we enable autonomy because teleoperation is foundational to building autonomous systems. What we've done now is launch a new category of these high-force actuators. As I mentioned, we're working with OEMs, tier 1 suppliers, and defense organizations. We're helping manufacturers transition from hydraulics to electric motion systems, and we're bringing the next generation of motion technology to real-world equipment. With that, let me hand it off to the next speaker.
Hello, everyone. My name is Mike Patterson. I'm the Director of Regional Sales at igus Inc. igus is a company that designs and manufactures motion plastics. We've been designing and manufacturing motion plastics since 1964 in Cologne, Germany. Here in North America, we were founded in 1985 in East Providence. We currently have over 500 employees all over North America, and we continue to both sell and manufacture the motion plastics for automation, including energy chains, flexible cables, linear guides, bearings, and robotic components. A couple of the products, I have 2 products and a BU, business unit, I would like to highlight today. The first product is one of our newest energy chain series. It's our larger series, the E4Q. Every motion, as you know, needs power and data. Our E4Q is the newest way to do that. It's much more user-friendly. It will protect your cables. It will extend the service life of the cables and the machine because the cables will last longer. It can run in high distance travel applications. Being that it's new, looking at where we're going in motion controls, it is stronger, it is lighter, it is built to go faster. It is an evolution of an older product. The next product I would like to highlight is our CF robot, our robot cable. Robotics is in its infancy, but as you know, that is one of the most difficult motions if you have any experience in robotics. The constant motion, the change of motion, you have to be prepared for that. Our CF robot cable does that. It's designed for torsion. It's designed for long-lasting performance in the most extreme conditions. This product will help your robot continue to do its job over time. And as you automate more and more of your factory, you need less and less people. You have to make sure that that machine is going to last, it's going to run. And then, of course, last, our business unit, Smart Plastics. As we use our products, which I would say are dumb products, energy chain and cables, they're just standard products. We've designed and created these smart plastic products, to work on predictive maintenance or preventative maintenance, stopping the catastrophic failures, saving you money. Again, as you automate more and more of the factory, you'll have less and less people there to monitor these. So having a system that can monitor the preventative maintenance. And then as we move forward into the predictive maintenance, telling you when a machine is going to break down or when it's time to change a product before it gets there, so that you can anticipate, you can schedule, and you can do that without any of those failures, without any of those breakdowns. So just the 3 things I'd like to highlight today. Thank you, everyone, and back to you, Rob.
Thank you, Mike, Hiten, and Matt. And let's go on to our program questions now. And so first question is, what should engineers consider when selecting motion control technologies that will still meet the needs of machines 10 or 20 years from now? Hiten, you want to take a crack at that?
Absolutely. Yeah. So the pressure on business is constantly to optimize for operating expense, right? And so as you start to think about the technology of the future, the key business interest is around total cost of ownership and reducing that operating expense. And as we think about technologies that do that, forwarded that are getting data so that you understand predictively how systems are going to fail, getting systems that have a lower failure rate, and certainly improving on energy efficiency. And that's what we're trying to do with RISE Robotics' belt-drawleg technology.
Okay, Mike, Matt, either one of you want to weigh in on that?
Yeah, from our standpoint, as far as selecting now for 10 from 20 years from now, I guess we tend to do things in when we redesign and design, we try to fit it in the same envelope so that as technology increases, as speed increases, you can switch out maybe what we sell today for what we'll sell 10 years from now, and it'll slide right into place. We kind of look at that universal connection, those types of things to try to look into the future.
Yeah, and I think for us, it's sort of similar. We look, especially for our technologies around control and development, expandability, adding computational capability, adding more nodes to what we do in terms of motion systems, while looking toward these adjacent technologies like maglev or other fundamental moving drive systems that we expect to provide advantages in the future. So yeah, this is, I think, really key, but yeah, behind it all, I think are expandable real-time control systems that can address these increasing loads of computation for complex motion systems.
Okay, great.
And as a happy customer of igus, I can say that we definitely have experience with their products, and we've also found that the improvements that they're making to their technologies help us build products that are smaller, right, which reduces even the capex cost of the goods that we're selling, which has been fantastic.
Okay, terrific. Okay, next question. What role does condition monitoring play in helping warehouses move from reactive maintenance to predictive maintenance? Mike, you want to give a crack at that?
Yeah, I touched on a little bit with my smart plastics presentation, but like I said, as these manufacturing facilities, warehouses, they all move to more automation, you're seeing a reduction in labor and people looking over a machine. So, preventative maintenance is great, but being able to predict when a machine is going to go down or when it's time to change out items is going to be absolutely massive, and with proper testing and proper data and, hopefully AI getting better, we'll be able to look at that system and tell you exactly when it's time to change something out so that you never have downtime and you don't have those unexpected costs and downtime and everything that is tied to that.
All right, Matt or Hiten, want to weigh in on that?
Yeah, let me take this one also. So what we've done with our actuators is certainly, as Mike described, that definitely is a trend. There's this tremendous amounts of interest as there are fewer workers. How do we reduce the total amount of maintenance? Because if you still need the same amount of maintenance and you still need the same amount of people looking over the machines, you really haven't gotten all the gains that you could. And so our technology, which fundamentally has a belt on the inside as opposed to hydraulic fluid that can leak, has only one wear item, which is our belt. And what we're able to do is put electric current through the steel that's inside these belts and actually monitor them for wear. And we're able to tell our customers when the belts are aging and that it's time to proactively service the machine. So they don't even have to schedule preventative maintenance. It's the next time you have downtime or a shift change, it's time to service this machine. And we're thrilled to be able to do that because moving to on-demand maintenance, as we call it, is the holy grail of cost efficiency for businesses.
Right.
Yeah, and I think for us, adding to that, sort of a part of our design, especially when we start to talk about algorithmic intelligence and these different applications, we've transitioned toward non-wearing components. Typically, the load-bearing elements of precision motion systems can create this kind of maintenance schedule that's required to potentially change or that could affect that for predictive maintenance. And we are doing that. But I think a part of the intelligence of what we're doing is we're using systems that don't really require maintenance in many cases, or they're non-wearing, or they're using, for example, air-bearing technology, which principally just floats and there's no rubbing, rolling, no fatigue. So in cases like that, especially where we know that that's going to be the application that runs on hard duty cycles, you'll find in our designs, those designs don't have wearing elements, or in many cases, there's really no maintenance.
Okay, great. Talking about algorithms, how do process algorithms influence purpose-driven mechanical design, Matt?
Yeah, so this goes right into the topics or the questions that preceded this one. A lot of what we're doing to provide unique value propositions with our precision motion equipment is to embed this algorithmic intelligence. And increasingly for us, understanding the strategic end process of what's required for these markets is to develop the mechanics in combination with the algorithmic intelligence. For example, in my group, we have design engineers and we have algorithmic developers, and we sit in the same meetings, we do the same group collaboration, and it becomes something that's a solution for a problem. Maybe historically, motion control was developed with fundamental aspects. Now it's being adapted with more sophistication related from the build-up mechanical design with the algorithmic intelligence understood that it's going to play with the mechanics. One example that's largely going into data center is this optical interconnectivity. And so inside my group, we're looking at what's really required and what we need to do to test photonic integrated circuits and things like this. And we're designing the mechanics around these patent pending algorithms that now we're developing and demonstrating in particular contexts. So I think this is kind of the future of what we do, where we have sort of a proprietary solution that runs these precision robotics, and the robotics are developed with the algorithms. This is something I think we're seeing more and more as AI starts getting traction and taking hold.
Okay, I want to weigh in on that, Mike or Hinton? Okay, Matt, you got that one covered. Is the industry ready for a new approach to high force motion control? If so, why? And I'll give that one to Hinton.
Yes, so what we're seeing is that there are increasing demands to electrify machines and to make systems more autonomous. And to do that, the fundamental technologies that are used have to be more efficient. If you take a diesel engine driven, hydraulic powered heavy machine, say a forklift, and you decide you want to electrify it, you typically end up doubling the price. And that's because the size of the battery to run a 6 to 8 hour shift is huge. And when we bring our technology in, we reduce the size of the battery in half. But that's not the only cost savings we provide. We also reduce the cost of the charging infrastructure by half. And we reduce the amount of electricity used. So we reduce the OpEx of the machine by half as well. The other piece is that these machines, there's a lot of interest in turning these machines into autonomous systems. And that's very challenging to do with a hydraulic system because you don't have any feedback. And it's nearly impossible to build a digital twin of that system. And so what we've done with our actuators is to provide all of the necessary data out of the box: position, health, force, orientation, that allows OEMs to build digital twins of these systems very easily. And with the digital twin and a drive-by-wire system, we were able to offer blue-collar workers the ability to work from home, because then they can operate the machine from their PC and they can see exactly how the machine's behaving. But then you can also add autonomy on top of that. You might have heard that Waymo, as automated as they are, still has a set of backup drivers that step in anytime the machines get stuck, and they help the machines get unstuck. And that's true for automated warehouse as well. And so we provide that foundational layer, which is in great demand right now as systems are getting more electrified and more automated.
Okay, want to weigh in, Mike or Matt? All right, Joe. What advances, precision is an important part of motion control, and what advances in motion control are having the most impact on precision? And anybody who wants can weigh in on that.
Ooh. So yeah, so we tend to attack with our application space. The arc is generally toward greater precision, greater dynamics, higher throughput requirements. So I think we see that I think along with this theme of AI, we're continuing to advance and embed learning, machine intelligence, adaptive algorithms that can allow for compensation impacts, especially in operating environments with vibrations or with other aspects like thermal drift and things like this. So I would say that's one of the biggest future looking capabilities that it's being developed at PI, to have this embedded intelligence on the systems to get the most of the mechanics. There's some talk of cost, and there's two ways to do things. One is mechanical, with sort of using the best of everything, the tightest tolerances, and to some degree adjacently to make corrections on equipment to get the most value add. And so I would say to some degree we're doing both, as this arc of precision keeps creating higher demands, or the arc of dynamics is everything's becoming more dynamics. But I think really from this aspect, this controls intelligence and adaptive algorithms and machine learning and AI are becoming a big part, a big influential part of what we're doing in these key strategic areas.
Okay, want to weigh in on that, Mike or Hiten?
Yeah, I agree with Matt that there is a lot of demand for increased precision. We've seen that a lot, where folks are trying to control hydraulic systems or build new systems, and then they realize that the core hydraulic technology can't deliver the precision that they need. Our actuators out of the box will do a few millimeters, and if the customers want it, we can offer even tighter precision.
Yeah, and it's probably interesting just to understand the scale. PI specializes in the deep end of precision, and we have some cases where we're sub-nanometer stability, which I think is hard for people to imagine, especially at conventional intuitive scales.
All right. As warehouses become more automated and machines are moving faster and farther, what are some of the reliability challenges engineers should be paying attention to? And I'll throw that one to Mike.
Yeah, thank you. The biggest challenge is obviously, I think, selecting the right products, understanding where you're at, what you need, and understanding the capability of that product. I guess is unique in what we do is testing. We test everything, and we test it in real world applications. We have one of the largest test facilities in Germany, definitely the largest in our field. And we run those machines under real world conditions, including, I see a question in the chat about extreme weather conditions. We have a freezer trailer where we run our product. We have an outdoor area where we run our product. And really, that's what you have to look at is, are you selecting something that's been tested and run and in a real world application, in that length, in that speed? You have to look at the whole package, and then you have to ask, are they evolving? A lot of our products in our realm, it's the same one. Again, I showed the E4Q, that's our newest product, where we reduced weight. We've also made it stronger because, again, things are going to move further, they're going to move faster. So we're constantly evolving our products, like Hiten spoke about, also smaller envelopes. So we build products to get smaller, fit in tighter envelopes, be less seen. Those types of things.
All right. And want to add to that, Matt or Hiten?
I would just go ahead.
Go ahead, Matt.
You go.
All right. Yeah. So in addition to when you think about maintenance, so in addition to removing hydraulic leaks and hydraulic maintenance in our machines, we also have to work with our customers to remove grease points, right? Because that's also something where if you already have somebody looking at the hydraulics before every shift, then it's very easy to have a design where you put grease in. Well, now when we work with them and we remove the hydraulics, well, they still need people to check the grease. So that's when we come to them and say, well, have you considered some products from igus to eliminate those grease points? And we had a lot of success in our products as well, eliminating anything that needs to be lubricated by using the right kind of plastic and making sure that the plastic lasts the life of the product.
And yeah, I would just kind of add to that similar themes. When we go to certain applications, we'll switch to air bearings. Air bearings are non-wearing by definition. They require no lubrication to that point. We are seeing things tending to be smaller. That's a request that we constantly get. We're shrinking everything almost daily. And when we have these smaller, potentially more fragile elements, that goes into the design and preventive maintenance and making sure the design is sufficient to operate reliably. So these are all themes that we deal with daily, I would say, and I get a request to make something smaller just about every day. So I get that for sure.
Okay, thanks. And thanks for answering one of the audience questions there. That's pretty good. Okay, what are some key features of a motion controller critical to future-proofing as processes move further into machine learning? You want to handle that one, Matt?
Yeah, so this is something of key interest for us. We're starting to develop algorithms that we're moving through patent that have a lot of aspects of artificial intelligence embedded in them. So there's been multiple applications on our side, and one of the keys is really the computational capability of the controllers. When you start to do many calculations with external synchronization, and you need to have everything running, evaluating, and acting according to these algorithms, you need a lot of computational capability. So from a control standpoint, we're continuing to increase the capacity of our controllers. There's a new release called the ACS eCPX. We're updating the cycle rates. We're now running the computations at a faster speed, which means higher throughput, which generally means more efficiency in the process. In the meantime, we're expanding the number of nodes for the number of axes that can be applied up to 128. And then we're moving to more cores in our processor and more memory. And so I would say this is really key. And along with that, you need a real-time deterministic control system so you can do all of this synchronously with quick evaluation and adaptive intelligence embedded. It's really what makes, in some cases for us, we've worked with partners, and we've improved our partners' process times by 2 to 3 orders of magnitude. And I think they didn't realize that this was even humanly possible in their process. So, and a lot of that falls again on computational efficiency, power, and algorithms that are really truly differentiated and what are becoming patented and proprietary to PI. But this is what I see, having a real-time deterministic compute capable system that can expand on nodes. It's really critical for future proofing. If you don't have that, you could be walking to a dead end.
Thanks, Matt. Any comments on future-proofing, Mike and Hiten?
Yeah, so what we try to do is we try to close the loop as much as possible in a very deterministic way in our actuators. And we recognize that companies like PI will be counting our determinism at the lower layers to provide the capability that they provide at their layer. And they need to be able to count on what we do. And they need to be able to work with our actuators at very high speeds and work with many of them. So we offer EtherCAT as an interface in addition to CAN bus to get to a higher node count, to get to tighter controls.
Yeah, from our end, like I showed the ChainFlex robot cable, having a product that is prepared to move in all directions. As as machine learning becomes more and more available and used, we can't always determine which way something's going to move. So we have to be prepared for all types of motion.
Right. Here's a fun one that everyone's having to deal with. In what ways has AI become a game changer in motion control? And whoever wants to start that, it's fine.
I'll jump in first. I think it's interesting. For the first time, we're starting to see, number one, users that are using AI trying to do coding and things like this for our motion control solutions or to interface with our own algorithms. In some aspects, it's partially ready. In some aspects, it's not really there. So it's good guidance, but I don't think it's absolutely reliable. The other thing I would say is we see huge demand along these strategic infrastructure growth for edge AI and data center that are really critical. And then finally, for us, sort of developing our own AI embedded in our control solutions for these strategic processes that support that has been a huge thrust for us. And that comes right again to one of the previous questions. How do we design a mechanical system to execute that intelligence? So it's really now becoming a little bit of an ecosystem where we're serving the community of AI companies while also having our own really proprietary AI to help push their AI. So yeah, it's now a part of our everyday lives, I think, to an extent, and maybe not still has work to do is the way that I would put it, but that's how it's changed for us.
For heavy machines and humanoid systems, one of the key ways in which companies are writing code now and training these AI systems is a process that's called sim to real or real to sim. They start with something that's real, make a digital twin out of it, do all of the training in a virtual environment so that they can do it in parallel, and then transfer the neural network that's been trained into the end machine. And so the core capability that they need is getting to that digital twin. And that's where we put a lot of our focus on, is to make sure that our systems are deterministic, but also that they can be modeled digitally very easily, making it possible to model not just our actuators, but also the full system. And then you can put it in simulation and then operate it that way.
Yeah, if I could add to that, this is really an important aspect that Hiten touched on, and it's the same, some of the topics he said, like EtherCAT, we use EtherCAT, what he's talking about, digital twins. We have a full simulation. I can say that in our group, we had 3 months until hardware arrival. We had a process development, and we used this digital twin simulation to make a signal simulator and mimic the whole process, have it learn. And then when it was delivered, the hardware was actually delivered. It took 2 days to completely have this 4-month development working. And so on our control systems, we have a simulator that carries all this on board, deterministic intelligence to make simulated signals and execute. And with reliable information and data, which I think is really a key use. As companies, we're starting to gather and collect this proprietary data and use it for simulation, and it's not widely available. So yeah, you get very specialized intelligence in some of these things. Yeah.
Same with us, family. Last one, you're collecting 50+ years of testing data, and putting it in a location, and now you'll kick out product improvements, better predictive maintenance calculators, all of those things, and being able to share with our customers.
Great. Okay, as equipment becomes more electrified, connected, and autonomous, how do the requirements for motion control change? Where do traditional hydraulic systems begin to create constraints? Hiten, you want to take that?
Yeah, so as I touched on this before, electrification is really held up by the inefficiency of heavy machines and hydraulic systems. Because again, it makes electrifying the systems unviable. And so by developing motion control that's a lot more efficient and can still deliver the forces that hydraulic systems can deliver, you're able to transition legacy hydraulic systems into electric. The second piece is about connected systems. And one of the challenges with hydraulic systems is that you don't really have any data. Matt had touched briefly on what you can do when you're able to collect data and how you can use it to train systems. For us, the connectivity, as I mentioned, enables teleoperation, which is like foundational to the next item that we're going to talk about. But it also allows our customers to optimize their machine builds. Usually, if you under-design an actuator, so if you have an excavator, and I picked that because those machines get stressed a lot, but if you have an actuator or a joint that's under-designed, you find out very quickly in the warranty claims that are coming in and the replacements that you have to make. If you've over-designed something, you don't know. And when you can collect data, you can find out which aspects of your machine are over-designed so that the next iteration of the machine, you can shave off additional material or an oversized joint and actually lower cost, which ultimately ends up helping the manufacturers make more money, but also makes the equipment more affordable for their end customers. And then the third piece for autonomous systems, the systems have to be stiff and easy to control, not sloppy and squishy like hydraulic systems. And then on top of that, as I mentioned, the importance of digital twins and getting that in place. And so we're able to address all three of those aspects of the next generation of machines with our actuators.
Okay, thank you, Hiten. Any want to add to that, Mike or Matt?
I would just say I think these are all excellent points. Hiten touched on stiffness, and I think stiffness is key in the repeatability of systems to do this kind of autonomous, reliable operation. And like Hiten said, really, if you understand the signals, the data, you can design to optimization with the correct costing structure. And I think, these are really key, especially with digital twins and having sufficient data.
Gotcha. Okay. Many facilities are adding more robotic picking and palletizing systems. Once you've solved the motion control challenge, how do you ensure the cables and energy supply systems can survive millions of robotic movements? Mike, you want to take that?
Yeah. I've already touched on it. Testing all types of motion, continuous testing. igus is unique that early last year we rolled out a 4-year chain flex guarantee, and the only way you could roll out a 4-year guarantee is to test it for 4 years. I would imagine 5 years from last year we'll roll out a 5-year guarantee because they're going to prove it out. But as I said before, robotics being in its infancy, we talk about AI, machine learning. Again, I want to touch on, you have to be ready for all types of motions. Our chain flex robotic cable, it is built for torsion. It is built for all different directions. Currently a lot of the continuous flex cables are built for linear motion. That's great, but robots don't move in linear motions. I see the same robot doing a million different movements to do the same thing almost weekly, and that's going to continue to increase. There's no single way to do it yet. So you have to be prepared for that. And the best way to do that is test it for all types of motions and then guarantee it.
All right. Thank you, Mike.
Let me
Okay.
add just briefly to that. And we really appreciate it when our suppliers can give us that kind of guarantee, because usually, so we build linear actuators, but we also build full systems for the Air Force. And we have a liftgate product that we're white labeling, working with our partner, Anthony Liftgates. And we want to be able to offer a lifetime warranty on the product. And that's only possible if all of the wear items also come with lifetime warranties, because we don't have the time to do that testing. So when igus says, hey, we're going to give you a 4-year warranty on the chain, we know that we can pass that on to our customers, and that's very helpful. Because we're able to do things like batteries these days. Lithium iron phosphate batteries last 3,000 cycles, but you can get them to last 10,000 if you manage the energy. And so we're constantly looking at ways, how do we extend the life of these machines so that the initial CapEx is justified in the total cost of ownership, which companies are always looking to bring down.
And if I can add, at PI, we're also a customer of igus, and we appreciate that as well. And certainly for our systems, it might be non-wearing the cable, flexing over many iterations, and how to manage that is really key. And we appreciate this kind of lifetime work from companies like igus.
All right. Thank you so much for this great discussion. And now we're on to the question and answer portion of our event. To participate, click the Q&A icon in your navigation center and then just type your question into the available text box before clicking send. If we're unable to answer all submitted questions during today's webinar, we'll be sure to share them with our speakers, who can reply to you offline. And so with that, we have a ton of questions today. And first one is, could it be possible to implement the chain flex cable technology in an off-road machinery with extreme weather conditions?
Yeah, I touched on it a little bit, Rob, but yes, it can be. We have cables all over the world, including up in the frozen tundra on top drive oil rigs and all over the desert as well. We do have a limit, of course. We've tested it to that limit, but generally we've seen success outside of that as well. Yep.
Okay. Anyone? Okay, here's another one. What kind of applications do you see still practical for hydraulics going forward?
Yeah, so initially any new technology like ours is more expensive than hydraulic systems. And so where we make the most difference today is in applications that have high utilization. So industrial hydraulic systems that are running 24/7 fail often, and we see an easy path in. On the other end of the spectrum, you've got hydraulic systems that are used in consumer applications and are used maybe once a week or twice a week if you have a tractor in your backyard that's not going to get that kind of usage. And so for those systems, because they're used so infrequently, you're not really stressing the seals, you're not really stressing the system, and they can last for a very, very long time. And so I see that for consumer applications, hydraulics are going to continue to be practical for a long, long time. Eventually, we'll come for those as well. But for now, we're focused on high utilization applications.
Okay, thank you. Being that there is a cost associated with maintenance, is there specialized education required for changing a part during, say, a shift change? How about during a shift? Anybody want to take that one? No. Educating
I'll
your
try that.
users?
Yeah, so our actuators have one wear item that everything else lasts the life of the product. We have one wear item, which is the belt. And we are able to tell our customers that the belts need to get replaced even before failure. And the process of replacing one of the belts is you open up one side of the cylinder, the service hatch, you connect the new belt to the old belt, and then you pull out the old belt and the new belt snakes into the system, and then you close it up. And that's roughly a 2-hour process. So it's very easy to do between shift changes and can certainly be done during a shift change. Although you'll rarely have to do it during a shift change because you'll know the check engine light will be on and you'll know that it's time to service the system at the next change.
Gotcha. Okay, here's another one on shifts. Being that 10-hour shifts are becoming the norm, how long does it take to change a battery or charge one? Anybody want to take that one?
I can speak to that. So the charge rate is really a function of the type of battery you're using and how much you're willing to pay for it. The most economic batteries these days are lithium iron phosphate batteries. Their maximum charge rate is half a C. So half a C to 2 C, depending on what kind you use. So you can charge them. Half a C means you can charge them in 2 hours, and 2 C means you can charge them in half an hour. And if you go to more esoteric batteries like lithium titanium oxide batteries, these batteries can be charged in 10 minutes. But sometimes it's not useful to pay the premium given that you could do some other battery in 30 minutes. So it's really a function of your budget and how important that downtime is to you in selecting the battery chemistry. You also need the charging infrastructure. So if you're going to charge a system in 10 minutes, you have to have a grid connection that's going to let you pull that much juice from the grid. And sometimes that's the limitation, not the battery in the machine.
Okay, gotcha. Okay, here's an interesting one. These are all good questions. I understand that optical reflective encoders and scales can get down in the nanometer accuracy range. Are you using these types of components in your products? Anybody doing that?
For us, yes, we use a number of sensor technologies, including linear scale encoders of different material composition. We use capacitive sensors, we use strain gauges, we use a wide array of the most high precision feedback encoding systems. But yes, linear encoders are one, especially low CTE linear encoders, and that's critical to a lot of what we do.
Okay.
I'll say that our products are used in all kinds of environments, and so we try to stay away from any kind of optical sensors unless we are confident that we can seal them very, very tightly. what I found in my past experience with industrial and military applications, it's very easy for these systems to get dirty. And since we're building heavy machines that don't really need that level of accuracy, we're able to get by with magnetic sensors.
Yeah, and this is a good point for us as well, especially for things that are in debris contaminated environments using linear encoders. We tend to use redundant scales. So in case there is contamination, certainly contaminated linear encoders are a concern, especially in debris-laden environments. So that's a concern of ours as well. And in some cases, we seal the stage to prevent the encoder access to external debris and purge. And anyway, but it's also a concern.
All right, great, thank you. Okay, one last question. That is, how does external device and signal synchronization play into future processes, and how is this being addressed?
I can take that first. You can tell from the conversation that we've had in this webinar that we're doing a lot of work with external factory. Hiten mentioned EtherCAT. EtherCAT is one form to add additional network nodes onto real-time systems. Additionally, for us, whether it's line scan imagers, lasers, power meters, detectors, transimpedance amplifiers, the world of what we do is synchronized through external signals, and the machine intelligence that we're talking about, learning, artificial intelligence, all has to speak to those synchronously. And so for me, this is only something that grows from here. And the ability to integrate, deal, and to handle those signals synchronously with underlying algorithms on the motion control systems is really going to be critical for the future. So that's a big thrust of our work. And I think signal synchronization with external devices is a common theme for all we're doing, whether it's cable tracking, integrated machine intelligence, EtherCAT. It's a part of what we do every day, and it's only becoming more of that.
All right, thank you.
I want to second what Matt's saying, is that the importance of this is increasing because as systems get more automated and they have multiple axes, making sure they don't collide into each other and being able to figure out where the systems are in real time has become super important. So far, most of our customers have only asked for EtherCAT beyond CAN, but we're open to all kinds of technologies that are really, for us, would be customer driven.
Okay. All right. That's all the time we have for questions today. Thank you. We appreciate our speakers' time and expertise on today's topic. Thank you to our sponsors, igus, PI, and Rise Robotics, as well as to everyone in the audience. We appreciate your attention and participation. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers to learn from this session. On behalf of our guests, Matt Price, Hiten, Sonpal, and Mike Patterson, I am Rob Spiegel. Thanks for your time and have a great day.
Thank you, Rob.
Thank you, Rob. Thank you, everyone.